Welcome to another episode of Dave Does Math from Home. Today we are talking about section 2.7, which is about function inverses. There's a lot to say about function inverses, and we'll get to that. But first I want to talk about inverses in general. So the question I always like to start out this lesson with is, what is the inverse of 3? This is a really fun question to ask a classroom full of students because half of them will say that the inverse of 3 is -3, and the other half of them will say that the inverse of 3 is 1/3, and then you can have a really big argument about it, which is most of what doing math is about, having big arguments about things. So I like having this discussion in class. We're not in class. This is a YouTube video, so we're going to have to do the best we can. Please pretend that you are arguing about which of these is the inverse of 3 for a moment. Before I get to tell you that they are both the inverse of 3, this is the additive inverse because 3 plus -3 is 0, and 0 is the additive identity. This is the multiplicative inverse because 3 times 1/3 is 1, and this is the multiplicative identity. Oh, I'm spelling identity wrong. No one saw that. This is fine. Let me try and block some of this glare. So they're both the identity of 3 because 3 has two identities. It has an identity for each category of operation because each category of operation has a different identity. 0 is the additive identity because adding 0 does nothing. It doesn't change the number. If you start with a number, you can add 0 to it to get that number again. That's why it's the identity. It tells you what that number is when you add 0 to it. 1 is the same for multiplication. You can multiply a number by 1, and it does not change that number. You get the same number out if you multiply it by 1. So there are two different kinds of identities for the two different kinds of operations. And that leaves us with two different kinds of inverses. And this is for numbers. Now let's take a moment to talk about functions. Let's say I have a function f of x equals 2x minus 3. This is a nice little function. It does things. What is the inverse? At this point, it's probably pretty tempting to say that the inverse of this should either be -2x plus 3, maybe? Or maybe the inverse of this is 1 over 2x minus 3, maybe? And these are both excellent guesses, because both of these things are a kind of inverse for this function. This is the additive inverse. If you add this to this, you will get 0. 0 is the identity, and that's interesting. This is the multiplicative inverse. If you multiply this by this, you will get 1, and that is the identity. So each of these is a kind of inverse for this function, but neither of these things is what we're typically talking about when we say function inverse. And that is because when we're talking about functions, the operation that we're interested in is not addition and it's not multiplication. The operation we're interested in is function composition. It's like we talked about in section 2.6. We want to be able to put one function inside another function, and we want the result to be the identity function. We don't want the additive identity. We don't want the multiplicative identity because we don't want to add these functions and we don't want to multiply them. We want to compose the functions and we want to get the function identity. That's what we're talking about. So both of these are great guesses, but they're not the function inverse. The function inverse for this, and we'll go over how to find a function inverse in a little bit, but the function inverse for this is x plus 3 over 2. And I will show you why. F of g of x, in this case, is going to be, let's look at what f does to things. It multiplies things by 2 and then subtracts 3. So if the thing it's doing this to is x plus 3 over 2, if we start to simplify this, we'll cancel the 2's, and then we'll have x plus 3 minus 3. That will just be x. This is the identity function. F of x equals x. This is the identity. Because, I'm going to try to block some glare again. Earlier I described the identity as the do-nothing operation. Adding 0 is an identity because adding 0 does nothing. Multiplying by 1 is an identity because multiplying by 1 does nothing. This is the identity function because it changes nothing. Whatever x is, that's what the function is. You plug in 3 into this thing, you get 3 out. You plug in 752, you get 752. This is the identity function. So this is the goal for function inverses. If you have a function and you're trying to find the inverse, you want to find the function that you can stuff inside of your original function so that when you simplify everything, you just get x. That's what's going on here. The slightly tricky part is we kind of have to do it twice. In section 2.6, we talked about how function composition is not commutative. So f of x, or f of g of x, is not always the same thing as g of f of x. So if we want to verify that something is the identity, we got to do it twice. So we've already done f of g of x, so let's do g of f of x. So let's look at what g does to things. G is going to take a thing, it's going to add 3, and then it's going to divide by 2. This is g. Inside of this, we're going to put f, so 2x minus 3. And now you start canceling things. The 3's cancel first, and then the 2's cancel, and you just have x. So, this is what a function inverse is. This is how you verify that something is an inverse. You compose it any which way you can to try and get x as a result, because x is the identity. Let's talk about how to find a function inverse. There's 2 ways to do this. There's the book technique and the Dave technique. I'm going to show you the Dave technique first because I like it better. Let's start with something like f of x equals 7 times x plus, I already used 3. Let's use 7 times x plus 4. If I want to find the inverse of this function, what I do is I make a list of what is happening to x. So imagine that someone gave you a value for x, and you were going to evaluate, like, say you were going to evaluate f of 5, for instance. Imagine what operations you would perform to the number 5. So you would start with 5. The first thing you would do to that number 5, if you were going to evaluate this function, is you would add 4. And then the second thing you would do to that number, whatever the outcome was, is you would multiply by 7. This is what the function f of x does to things. First it adds 4, then it multiplies by 7. If I want to create a function inverse, I need to do the opposite of these operations, and I need to do it in the opposite order. So the first thing that g of x needs to do as a function is, I'm going to go through this list backwards and reverse these things. First thing it needs to do is divide by 7. The second thing it needs to do is subtract 4. So we can create a function that divides by 7 and then subtracts 4. It'll be x over 7 minus 4. And then we can check this. F of g of x should be 7 times something plus 4. And into here I'll put x over 7 minus 4. So we can see right away that these 4's will cancel, and then we can see that 7x over 7 is x. So yeah, works that way. G of f of x should be something over 7 minus 4. And inside here we're going to put 7 times x plus 4. So, 7 times the quantity x plus 4. So now these 7's cancel, and then x plus 4 minus 4, the 4's cancel, and we just have x again. So this is the Dave technique. Make a list of the things that are happening, and then undo those things in the opposite order. I'm going to do one more example of these things, and then I'll show you how the book finds inverses. And then I'll do the one example that's really hard. So let's make something a little more interesting. Let's say that f of x equals the cube root of x plus 8 over 5. So if we're making a list of all the things that this function does, it starts out by adding 8, and then it divides by 5, and then it does a cube root. Those are the 3 things that this function does in that order. So if I want an inverse, I will need my inverse to, the first thing I need my inverse to do is cube my number. So I'll have an x cubed. The second thing I need my inverse to do is multiply by 5. So I'll put a 5 out front like this. The third thing I need my inverse to do is subtract 8. So this is my inverse. We can check it. F of g of x should be the cube root of something plus 8 over 5. And in here we're going to put 5x cubed minus 8. So the 8's cancel, and then the 5's cancel, and then we have the cube root of x cubed, which is x. G of f of x is probably going to be the same thing. It's going to be 5 times something cubed minus 8. And the something is the cube root of x plus 8 over 5. So parentheses first. The cube of the cube root cancels. And then we have x plus 8 over 5 times 5. Multiplication comes next. And then we have x plus 8 minus 8. That's just x. So this is, I think, the easy way to get function inverses. Not everyone agrees with me, so I will show you the other technique as well. I can do the other technique to this thing. That'll save me the trouble of checking it. The way that the book suggests that you find function inverses is if you start the function that we want to play with, if we start with this being y equals some function of x. The book's suggestion for finding an inverse is switch x and y and then solve this equation for y. So if we want y to be isolated, the first thing we would have to do is cube both sides. So we'd have x cubed equals y plus 8 over 5. It's also worth noting that the first thing we did for g was cube. So the first thing we do here is cube. The next thing we do is multiply by 5. That'll give us 5x cubed equals y plus 8. So when we were doing this with Dave's technique, the second thing we did was multiply by 5. That's the same thing that's happening here. And then we subtract 8. So we get 5x cubed minus 8 equals y. This is the function inverse, which is the same thing we got, and we got there with the exact same set of steps and operations. We just dressed it up a little differently. So let me do one more example of getting a function inverse using the book's technique. Let's say we have y equals x minus 4 cubed over 6 plus 2. So using the book's technique, we would switch x and y. So I would say that this is x equals y minus 4 cubed over 6 plus 2. And then I would start solving this equation for y. So the first thing I would do is subtract 2. So x minus 2 equals y minus 4 cubed over 6. Then I would multiply by 6. So 6x minus 2 equals y minus 4 cubed. Then I would take the cube root of everything. So I have the cube root of 6x minus 2 equals y minus 4. And then I would add 4. So the cube root of 6 times the quantity x minus 2 plus 4 equals y. And this is the inverse. I'm not going to check this one, just in the interest of time. I do want to talk about one of the equations that's sort of just uncharacteristically difficult to find inverses for. Well, it's uncharacteristically difficult to find inverses for using my technique because it's very difficult to describe the operation that's happening. I guess using the book's technique is probably fine. The function that I'm talking about is something that looks like f of x equals 1 over x plus 3. This is a difficult function to find an inverse for using my technique because of how difficult it is to describe this 1 over situation. So if we're using Dave's technique, the first thing that happens is we add 3. That gives us our x plus 3. The second thing that happens is you put it under 1. Or you divide 1 by it, which is a very difficult thing to say here. The best word to use to describe this is reciprocal. So we took our x plus 3 and we made it 1 over x plus 3. That's how you got the 1 over bit. That's the best way to describe this if you're using the Dave technique. The nice thing about this is once you realize that this is just a reciprocal operation, the inverse of the reciprocal operation is reciprocal. So that's kind of nice. So g of x should be, first thing we need to do is reciprocal. So that'll give us 1 over x. And then the second thing we need to do is subtract 3. This is your inverse. if you're doing this problem, the book's technique, y equals 1 over x plus 3. This is, you would switch the x and y and say x equals 1 over y plus 3. You kind of have to still do the same thing. Maybe you multiply everything by y plus 3 and get y plus 3 times x equals 1. And then you divide everything by x. So you get y plus 3 equals 1 over x, which is functionally the same thing as just taking the reciprocal of both sides. But you can get there by multiplying by y plus 3 and then dividing by x. That's also fine. And then you subtract 3 from everything, and you get y equals 1 over x minus 3. So when you see these 1 overs, please think of them as reciprocals instead of like dividing by a thing. When you see like x over 7, that's a simple operation. That's you dividing by 7. 1 divided by the thing is a much more difficult operation to write down here. So the word you want to use is reciprocal for that, if the x is in the denominator. So we're already at about 22 minutes, so I'm going to cut the video here. There won't be a part 2, I guess, so this is the only part. I hope this was helpful.